Se qualcuno può chiudere la porta, iniziamo. Ok. Last
but not least.
Ultimo, più bello. Alessandro ci parla del suo emulatore del Commodore 64.
Is there anyone who doesn't understand Italian? Maybe we can switch to Italian because... No, English. Okay. Okay. My name is Alessandro Abbruzzetti. I am an engineer, a software engineer. I started programming when I was 12, when my parents purchased me my first computer, naturally a Commodore 64. And it was a great time because I started programming, and this event changed my life because opened me a lot of doors and also opened up my mind, and because in that period was hungry of knowledge and computer science knowledge. And so I started programming in the early 80s. In particular, I programmed in BASIC and assembler for the Commodore 64 games, utilities, stuff like this. And today, I work for Ericsson, one of the world's leaders in telecommunication infrastructures and services, and where we build software for, my area is, I work for Telecom Italia usage area, where we build software for, especially for back-end mobile services. And my team and I began to discover Scala a few years ago. I don't remember exactly when. We used the 2.8 version of Scala, so a few years ago. And when I was searching was a new way to develop software, because I was boring about Java. Yes, boring about Java. And when I found Scala, I was astonished. I was astonished because of its beauty and elegance, and especially for its new paradigm, the object-oriented and functional paradigm. Okay, so we can start this presentation. I want to split this presentation in two parts. The first one is the boring part, about the ins and outs of the emulators. And the second part, the last 50 minutes, maybe more or less, a live demo. So we will see a live demo with the emulator emulating a real game, and we will see later a demo scene, maybe one of the most difficult software to emulate, because the programmers that program this kind of scene, demo scene, try to use every tricks that the graphical chip, the VIC, can provide to you. Okay. I want to be clear with you what we are not talking about on this presentation, so you are being warned. No Scala time system, no Scala DSL, no libraries and frameworks, plug-in play components, category tailor, ACA, actors, future reactive. All of this, I'm very sorry, but you will not see anything about this. Think different. Okay. What we are talking about. So, in computing, an emulator is hardware or software that enables one computer system called the host system, so my laptop in this case, to behave like another computer called the guest, in this case the Commodore 64. An emulator typically enables the host system to run software or use peripheral devices designed for the guest system. Emulation refers to the ability of a computer program in an electronic device to emulate or imitate another program or device. I want to emphasize this word, imitate, because it reminds me a movie that I saw this winter, The Imitation Game. That is the story of Alan Turing, one of the father of computer science, and the story of its machine, the Turing machine. And in particular, the universal Turing machine maybe is the first example of emulator, because the universal Turing machine, you give to the universal Turing machine an encoded form of another software, of another machine, Turing machine, and the universal Turing machine emulates, behaves like the given input. So maybe it's the first example of an emulator. There is a difference between an emulator and a simulator. The emulator needs always the original software of the emulated system, and most of the time you need a dumping method to extract from the original system, for example, the operating system, the characters, all the information stored in the ROMs, in the read-only memories. So it's very, very different, the emulator and the simulator, because with a simulator you can bypass this needing and implement in a different way what we are doing to emulate. The emulator can be useful. The emulator can be useful too. For example, combat obsolescence, because I don't know how many of you have in your house a Commodore 64 or something like this, or an old gaming console. So this is a way to refresh in a new way the old things. Have better graphics quality, because it's obvious that the graphic cards of nowadays are better than the one of back then. And allow users to play games for discontinued console. This is an example. And add features original hardware didn't have. So, for example, you could add new cards that can be inserted in the virtual Commodore 64 and add new features. Why emulate a Commodore 64? You are thinking about this. First of all, because it's not easy at all, and I like challenges, and because it's funny, and you maybe at the end you will understand why, and because there is a huge amount of available software for it, because in the last 20 years, a lot of developers made reverse engineering of the original software, put this software on digital device of this period, and so we have a very huge amount of available software. And also because still today, it seems incredible, but there is an active community of developers and internet sites. A lot of crazy people still continue to develop for this platform. And in particular, there is an area called the demo scene. What is demo scene? The Commodore 64 demos are basically demonstrations. Okay, we are cool, or what can be done to push the limits of the Commodore 64 computer, made by, in general, programmers, but also musicians and artists in general. So it was not unusual to find demos that displayed a single picture, because, as we will see later, the graphical chip was discovered later, not in the 80s. In the 90s, a lot of people started to investigate about the graphical chips and discovered a lot of undocumented features of this chip. And based on this, very crazy programmers started to show to the others how can be possible to go beyond the limits of the graphical chip. This is the Commodore 64. Maybe someone of you remembered this case, and it was called the bread bin model or the bread box model, and it was beige. I don't know why, but strange color. And this is the startup screen with the ready prompt with the flashing cursor. Most of you are maybe wondering, but ready for what? Ready for accepting commands like your usual Scala interpreter in the same way. So it is ready to accept immediate basic commands, or you can type basic program and then run it. This is the screen when you turn on the computer. So this is the internal operating system. But during the years, a lot of new and alternatives operating systems were made by programmers. One of these is almost famous, is the GEOS operating system. And as you can see, the look and feel remembers something else. Maybe the Macintosh of the 80s. The look and feel is pretty the same, and also the functionalities. A little bit of the Commodore 64 history. The Commodore 64 was and is today an 8-bit home computer, and it was introduced during the Consumer Electronics Show in Las Vegas in '82 by Commodore International. And in particular, it is listed in the Guinness Book of World Records as the highest selling computer model of all the time, and with about 20 million of sold units. And that's incredible, but most Commodore 64 have been sold than any other single computer system, even to this day. More or less 10,000 commercial software titles have been made for it, for all, including development tools, office, productivity application, games, a lot of games, for every religion, colors, for all. And at its peak, the GEOS, this one, it was the third most popular microcomputer operating system in the world, just after the DOS, the MS-DOS, and the Macintosh operating system. Why Scala? Because does not exist, obviously, a Commodore 64 emulator written in Scala. This is the first one. There exists a lot of Commodore 64 emulators written in Java, even in JavaScript, especially in C and C++. Because I love Scala and its ecosystem, that's another reason. Because an emulator written in C and C++ can take advantage of, obviously, low-level operations, and so it's too easy. And because I was curious about a Scala implementation's performance, and we will see that I reached the target. Okay. Here we are with the Commodore 64 emulator called Kernal 64. Kernal, it's it's a mistake in a Commodore 64 documentation, because the real name was Kernal, but the guys who was writing the documentation made a mistake, so it was Kernal, and remains forever. What we are going to emulate in this emulator? Obviously, we have to emulate all the main hardware chipsets and the memory, because if we want to replicate all the software written for this emulator, we have to be accurate in every single aspect of the real machine. So for instance, to start, we have to emulate hardware chipsets, so every chip of the real machine, the memory, both the read-only memory and the random access memory, all the internal I/O devices, like keyboard, the monitor, the joysticks, audio device, and so on. But it's not enough, because the Commodore 64 alone, it's unuseful. So we have to talk with the other external devices, like the floppy driver, and we will see that it's the hardest part to emulate, because the floppy driver contains another processor inside, so you can think about it like another computer, totally separated by the Commodore 64. There is the magnetic type data storage device, the old audio cassettes, the printer, and last but not least, the cartridges. And because the cartridges were a piece of hardware that you can insert behind the Commodore 64 and inject inside it new functionalities. You can expand memory, for example. The RIU RAM expanded unit is one example. We have to go faster. This is a summary of the technical information about Commodore 64. It was introduced in 1982 and went end of production in 1993, 11 years. If you think that today a mobile phone lasts maybe some months, you can understand why it was a very big success, this home computer. It was sold less than $600, and the CPU was 6510. That was a modification of the most popular 6510, okay, was a modification of the most popular 6502, contained, for example, in the Apple II or in the Atari systems. The clock was 1 MHz. It has a grid sound chip called SID, S-I-D, with 3 channels of sound and 9 octaves, 4 waveforms, and only 64 kilobytes of RAM. You can think that today, one empty document in Word occupies on disk an order of magnitude of maybe 16 kilobytes. So you can think which was the difficulties of the programmers back then to write software for this computer. The display, the graphics was its maximum capability 320 by 200 with 16 colors. It has a lot of ports for TV, type interface, a user port. The user port, you can compare the Commodore 64 user port with, for example, maybe some of you play with Arduino systems. So the user port can be seen like a micro controller where you can play with it. It has 2 joysticks, cartridge port, obviously, and a serial peripheral port to communicate with, for example, with the driver. Yes, with the driver, with the floppy driver. And the operating system was in a ROM by Microsoft, and it was the basic version 2. Where to start from to build from scratch this kind of software? Naturally from internet, because it's the main source of information. And a real machine will be welcome, but I sold it in the 80s, so I don't have it. 99% of this kind of information are available, but that 1% cannot be neglected because we have to be as much as possible near to the real machine. So that 1%, it's very difficult to implement because you have a lot of documentation about the Commodore 64 thanks to the programmers and fans in the last 20 years. But that 1% it's really a problem. And every component is too hard to emulate because we have to go deeply to understand the difficulty, but we have no time to see this. But there are 2 components very difficult to emulate. There are the VIC, so the video interface controller, and the disk drive. The circuit diagram is another piece of information necessary to go on, and we are going to see. These are the main peripherals available for the Commodore 64. We have the disk drive, the printer that can be talked to the computer, the main computer via serial bus, the cassette port to read and write on cassettes, obviously the output to the video display back then with the PAL and NTSC video systems, the user port we talked about before, the expansion port where you can put the cartridges, and control ports to play with joysticks, the light pen, and the mouse. Okay, we can go. This is the circuit diagram, and it's necessary to build from scratch the Commodore 64 because we have to deal with the signals that the chips interchange each other's. So here is the clock, one of the main components. He has a frequency of about 1 MHz. The main CPU, the 2 complex interface adapter that deals with the external devices for I/O, and so with the drive, with the control ports, with the keyboard, and so on. The video interface controller, the sound interface device for audio. This is the programming logic array, a sort of facade, to use object-oriented terminology, which manage all the signals interchanged by all the other chips in a unique place. The random access memory, the kernel and the basic ROM, and the character ROM. There is a ROM where all the characters are stored inside. And the others, the expansion port, user port, control ports, keyboard, the serial bus, and the connector for the cassette reader and writer. Okay, we go a step up from the ground, and we can show this set of chips in another way. We have to deal with a a lot of signals, but we can show here just some of them. One important is the interrupt signal, that maybe in your world are the callback, for example, in Scala. We can try to find a comparison with these days. And the gray bars are the bus data and the address bus. Yes, the bus data and the address bus. And in the upper part of the slide, we see the dynamic RAM. In the real computer, the dynamic RAM must be refreshed by the video chip, but in the emulator it's not necessary. And the ROM, one for the characters, one for the basic, and one for the operating system, the kernel.
Sorry, question.
Yes. Sorry, can you repeat?
The difference between blue and the red lines.
Yes, the red lines are simply interrupt signals. There are two types of different interrupt. The NMI is the non-maskable interrupt. Yes, you have studied. And a normal interrupt that the programmers can mask. Another step up from the ground, it's a sort of object-oriented class diagram. So the emulators is a sort of aggregation of C64 component that is the composite, the famous composite pattern. Below the C64 component, there are all the implementations that we have seen so far. So the whole Commodore 64, the clock, the CPU, the expansion port, the memories, and so on. Okay, let's start 50 minutes. Okay, I have to skip some slides. The memory is organized like this. The CPU sees the memory in this way. It's not a raw, a stupid array of bytes, but it's different because you can activate or deactivate some RAM in the same address of the RAM. So it's a quite complicated system that the engineers of Commodore built back then. 64 kilobytes of RAM, always available to the user, but not when the basic ROM, kernel ROM, or character ROM are activated. 8 kilobyte basic ROM, kernel ROM, 4 kilobytes of character ROM, and there is also the color RAM. This is a detailed view of the I/O system. The VIC, it's the graphics system, the sound interface, the color, and the two timers we've seen before, all above the characters ROM. This is a very basic trait for the memory. We have just two methods, important method, how to read, how to write to the memory, where is the start address of that memory, and how much is long this memory. Another implementation of the memory, because we have to split the memory in pieces. So this is an implementation of the memory called bridge memory, because it's split in pieces that can be put together. But we have to go very, very fast because we have no time. The memory implementation, we can skip this. The advantages of this implementation is modularity, is isolation, ease of modification. The disadvantage is mainly the performance bottleneck. For this reason, other emulators use a raw array of bytes. But if you look at the code, maybe you can change your mind and understand why I choose this other implementation. The clock, this is one of the main components. You have to deal with about 1 megahertz, so 1 million of clock cycle per second. And these clock cycles are divided by, in the rising edge of the clock, the video processor uses the memory. On the other side is the 6501 that uses the memory. They alternate the memory, the use of the memory. Like in the reality, the emulator has a single source of synchronization, the clock, and it's managed by one thread. Only one thread. Listen carefully, one thread only. And so if the thread is preempted by the host CPU, the emulator slows down. So you can see maybe in a few minutes why. And because it's very difficult to implement a multi-threading environment here, because all the emulator runs with one thread. We could use another thread to the drive, but it's near impossible because the communication between the two devices is so time constrained, so it's nearly impossible. The emulator runs in a main loop, and we have to calibrate how many cycles we process per second, because we have to match the exact cycles that the real Commodore 64 uses in 1 second. I mean, 1 million about. So the calibration piece of this software checks how many cycles are emulated in 1 second, and then use the brakes to go slower and to target the 1 million cycles per second. This is not true when I press the F8 key and the warp mode, and we don't use anymore the brakes. In this way, on this laptop, I reached the 500% of the real capacity, of the real speed of the Commodore 64, so 5 times faster in Scala. The emulator main loop. We have the scheduler, we have to schedule events, we have to display things on the video. We have to emulate the drives, the printer, the CPU. A lot of things with one thread. We have a scheduler inside where we can schedule events, and all the chips use this scheduler to schedule events. So we have a linked list of events, because in the emulator words, the time is the number of cycles that has passed since now. So we have a linked list of events. When, what to do. What to do is basically a function of long to unit as a function. And the next, it's the pointer to the next event. It's an ordered list of events. This is the clock ins and outs, but we have no time to see it. It's basically, the important thing is the variable cycles, because that variable contains the number of cycles passed since the beginning, the startup of the emulator. The CPU, these are the 256 possible opcodes of the CPU. We have to emulate all the opcodes. This is the main flowchart processed by the processor. We have to care about the interrupts, and we have to emulate the single instructions of the real machines. Every instruction is then split in micro program like this. This is a look inside the processor, deal with the memory, and we have 3 basic registers, A, X, and Y, the program counter, and all the instructions are represented with the Scala type function 1 unit, and each instruction, for example, the loading LDA of the accumulator is split inside like in a, not like, it's a state machine, and so every instruction is split in micro states that the processor must follow. And I have little more time, okay. The main components, other main components, the complex interface adapter has 2 timers inside, the timer A, timer B. The time of the day, it's a real-time clock, and it's basically a state machine, and communicate with a data port to the external devices. We can skip this because it's too complicated. It's the sound system. Just an annotation, we have to reach the 44,000 samples per second, because this is the frequency of the original Commodore 64. The VIC is the most important part of all the system, together with the drive. We have no time to go inside, but the video graphics interface manages basically the display that you can imagine like a collection of lines. The raster register plot these lines one after the other, and manage the interrupts and manage the sprites. I don't know if this term is strange for you, but basically they are graphics objects managed directly by the hardware. And the collisions between the sprites, the background, and between the sprites. This was the layout of the display, so basically the dimensions, and you can see that one character is displayed in one cycle. We have to skip this one, but it was here you can find all the functionalities of the drive. Another very, very hard part to explain, and because we have to emulate a rotating disk in software with the same synchronization used by the original one, and the real floppy disk of back then are available today in digital format in a D64 format, and you can find all the software we told before. How is organized the disk in tracks and sectors, and the speed is 300 rotation per minute. Disk zones we skip. Okay, how we exchange data between the Commodore 64 and the drive using the serial bus. We have just 2 signals, the clock and the data. In this example, the drive understands 0010 because the clock signals is the clock that synchronizes the data. So just when the clock is high, the drive understands what is present on the data. Go faster, go faster. This is the specification of the CAI2 data port. You can see that every single bit has a meaning, different meaning, and you have to emulate that single bit. So this is just an example. When you are writing or reading that location, that is the implementation. When you read that location, we have to deal with the bus, so with the attention, clock, and data. They are single bits. It's not so easy. I'm a little bit crazy about this, but I implemented also the SweetLink cartridge, a cartridge that permits you to navigate to internet. So you can go to the old bulletin board system, and it's very strange to see in the emulator that you can even go to internet. A little, just some notes about the performance problem that I encountered in my implementation. I had to avoid the use of simple private valor var x, but I used private this valor var x, because in this way you skip the, because the compiler translates the private val or var x in the, an attribute, a private attribute, and two methods for get and set this value if it's a var, obviously. And without this private and the use of the private this, I have improved the performance by 1 order of magnitude in this way. Then I use inline notation and all the obvious things, avoid loop for loops, use while, and avoid by name parameter, because the compiler produce by the C, under the covers a lot of stuff that slow down the, in this context, I mean, in this context, the performance. Okay, very quickly, the demo, and so. Okay, maybe we can try this. Maybe it's is it better? Okay. First, okay. It's a classic. I use an USB controller. You can see here the drive. This is the LED of the drive, and these are the track and the sector. I am an absolute beginner for this game, so that is the real speed, 100% with 50 frames per second. If I go in warp mode, now, okay. Sorry. Ok. E 2. Sorry, second time. Third time. So we have, okay. Go faster. And so on. Okay. It was made in 91, so it was one of the last games of this console, full of sprites, full of details. Okay. And now the best part, the demo scene. This demo scene is from the competition of last year. Yes, there is a competition for this kind of things, and it won. It won the competition. So, thanks. It's not mine. It's not mine. Kilobytes, remember. Il bello viene dopo. Normally you can put graphics on the border, but the border are used now, up and down. Not yet the side borders, we will see later. The last part. One thread, remember, one thread. Look at the side borders. Okay, we stop here. There is another disk, but... Thank you.
Non si poteva finire meglio. Bellissimo, grazie.
Anche perché ho rubato anche quelli che stavano di là, perché stanno qua. 1 year and a half in the spare time.
How many lines of code?
I don't know.
The problem of drive emulation was it's a question. I noticed that the emulation of the demo was loading data during the execution.
Yes.
So I think the problem was that the drive is also a computer.
Yes, of course.
Is this a problem?
Inside there is a processor.
Okay. Thank you.
How many lines of code?
I don't know. Really, I don't know. Really, no.
It's on GitHub.
Ah, yes. The last one. Thank you.
Thank you. Ok, grazie a tutti. Ci vediamo a Frida tra un po'.